All right, so good. This is my last lecture. So I decided, right, so what Sasha invited me to do was talk a bit about MHD, talk a bit about kinetics, just to give you a flavor for it. If you want some more advanced topics, that's what the notes were for and what the homeworks are for. And then he encouraged me, well, he said, you have 3 lectures, why don't you do something that's not just, this is groundwork, right? So I figured I don't know if you looked at this part of the notes, but I figured I'm coming to Russia. I haven't been to Russia before. Russia has a long history of interesting plasma physics. So I just picked some Russians and was like, well, Coma Growth, let's do Coma Growth turbulence theory. Zadovich, there's some nice work on dynamo, anti-dynamo theorem, and what's called fluctuation dynamo or turbulent dynamo. I'll talk about that. And then I was also talking with Lev. You have a series of problem generators that we wrote for the code that was distributed. One of them is Landau damping that you'll look at today. 2 other ones involve these instabilities called Firehose and Mir instabilities. Firehose instability is something that you can get out of Brzezinski equations. So I was like, OK, Brzezinski, there's another Russian. Trying to think about the Russians with the Mir instability, but I've forgotten right now. But anyway, I'm going to do what? Mironov. Yeah. There's also Sagdiev, but I think, yeah. Anyway, so they're all in there. Good. So what I figured was I'll start with Coma Growth theory. It's really simple. I'll just quote myself what I said in the notes, which is like any simple thing, it's obvious in retrospect, but requires a genius to actually point it out. You can get it in a single line by dimensional analysis and just some assumptions. And then I'll go from there briefly into something called Oreshnikov-Frightenin theory of weak turbulence. I'm not going to do the full theory of weak turbulence. It's very long, very detailed. One nice thing about it, though, is that it's based on the concept of turbulence just being an ensemble of waves, which are weakly interacting. And because of that simple statement, you can actually do a lot of analytic work with it, as opposed to with something like Coma Growth theory or fully developed strong turbulence, you can't really do a lot of analytic work on it. I'm just going to sketch out some ideas that actually hung around in turbulence theory for about 30 years before being overturned by Goldreich-Streethart theory, which I'll talk about briefly. So that'll conclude just the turbulence bit. And then we'll do what happens if you subject not a strong magnetic field to turbulence, but a very weak magnetic field to turbulence. And that brings us to dynamo, and I'll talk about Zadovich and some contributions there. And then we'll get on to Firehose and Mir, which will help with, I think, what Lev will do tomorrow with the code, which is you actually do Firehose and Mir instabilities with the code. So with that intro, so Coma Growth. So like I said, it's very simple in retrospect. It's just dimensional analysis. The idea is that turbulence takes place in this plane. And the idea is that here's some wave number, just 2 pi over some scale of some fluctuation that you're interested in. And at very large scales, you go pumping energy into the system. So the classic thing that everyone always says, you take your coffee cup, you put a spoon into it, and this is the spoon scale, right? So this is where you start stirring. And I'm just going to visually sketch the assumptions that go into the theory. The idea is that there is an outer scale. So this is called an outer scale. It need not be particularly homogeneous or anything. It's just there is some outer scale where your spoon lives. And the idea is that through interactions between different eddies that you excite when you stir, you get a cascade. So this is called a cascade. And the assumption in Coma Growth is that whatever amount you're driving, so there's some energy input, which is epsilon. This energy is just channeled from scale to scale to scale to scale down to smaller and smaller scales conservatively. So I'll just sketch this like this. And this part right here is called the inertial range. And there is no special scale in the inertial range. It's completely conservative. You just pass the energy downward and downward and downward to smaller scales. You can picture this in the case of hydrodynamic turbulence by just eddies shearing other eddies apart. Right? You just stir your coffee cup and you see the production of smaller and smaller scales as time goes on. We all know that eventually that stops. There is some kind of dissipative scale. And that's, here's the dissipation range. So you keep conservatively passing the energy down the cascade until some point viscosity, say, in a hydrofluid becomes important. The reason why viscosity becomes important is because if you go back to the momentum equation, you have the left-hand side, which is just acceleration of a fluid element. Remember, inside this time derivative, there's a nonlinearity. So it's just a normal time derivative. And then there's this nonlinearity that had to do with flows carrying, flows advecting other flows. And that's what gives you the turbulence. And then there's a right-hand side that might have gas pressure in it, whatever else you want. What I didn't write in my ideal MHD equations was viscosity. So there might be something like that where there's some dynamical viscosity. And what you can see is that, suppose that mu were really, really small, as it is in pretty much every single astrophysical plasma. Like Phil was saying, the molecular viscosity in astrophysical plasmas is very small. Well, how do you activate this term? You just make the gradients large, right? And that's exactly what's going on here, right? You're making larger and larger wave numbers, which correspond to smaller and smaller scales. And even though this is small, there is some scale on which this term is finite. In the inertial range, so this is this viscous term is completely ignorable in the inertial range. That's the assumption. The assumption being that there's a wide range of scales between the stirring spoon and the place that you actually take out the energy. And that's it, right? That's really, really simple. There's an outer scale. There's an inner scale or a dissipative scale where, because of the largeness of the gradients that you create by making smaller and smaller scales in the flow, regardless of how small this is, there will always be a k where this term is finite. You just go to higher and higher k until this is important. And then as soon as this term starts competing with the nonlinear term right here, which is responsible for the cascade, you're no longer in the inertial range. And the only other thing is that the inertial range is conservative. So whatever energy that you're pumping in, there's just a constant energy flux from K shell to K shell to K shell to K shell down to smaller and smaller scales. And that's all you need in this theory. The actual quantitative details just come from dimensional analysis. The fact that there's no more ingredients in this picture completely, that's all you need. You can get everything from just what's on that board. And the reason why is that there's a single time scale, there's a single length scale, and there's a single velocity scale in the problem. That's given to you, right? So out here at the outer scale, there's some fluid flow, fluid velocity u at the outer scale. The outer scale is denoted by L. And the only way you can make there's nothing else, right? These are the things that you control. You stir on some scale. And there's only one time scale then that's implied that you can make out of this, and that's just L over U. So this is like a power which is being injected, and it has to have these units. And the only way that you can make these units is just with U squared and L over U. And then the only other ingredient is that if I take the energy in any wave number and I sum this over all wave numbers, I know I need to have the total energy which is in the fluid. And I just say that this is something like U squared, right? This is the kinetic energy. And if I sum over this energy spectrum, right? So this part here is called the energy spectrum. I know that if I just integrate that energy spectrum over all wave numbers, it just has to be the total kinetic energy in the system. And this is all you need to get this scaling. And I'll show you where this comes from just in a second. So this is just saying the energy in some K shell, first of all, it goes down with K. That's why I drew it the way I did. So this slope right here is minus 5/3. And of course, it's some function of how much energy I'm pumping into the system. So the more energy I pump in, there's more power in each K. So that makes sense qualitatively. The reason why this is imposed on you just comes from dimensional analysis. So if you say I have some energy spectrum, and I'm just going to sum up all the wave numbers up to some scale, I know this has to be something like this, the amount of kinetic energy at that scale. And the amount of kinetic energy at that scale, if this is a constant, I know what it is, right? Because I know what this is at the outer scale. It's just U squared over the only time in the problem, L over U. And if it's constant the whole way through the cascade, that means that this has to go like, lambda to the 2/3. So it's do you see that? So this is, you get U cubed here over L. If this is constant, U has to go like L to the 1/3. And if that thing is just fixed, that scaling holds all the way down the cascade. So that means just U squared is lambda to the 2/3 at every scale lambda. And the only way to satisfy this is just if this goes like K to the minus 5/3. And that's the Coma Growth spectrum. And there's really nothing much more to it than that. The only thing I'll draw your attention to is that the fluctuations, I guess I'll put a delta for a fluctuation. It goes like this. So if I take, what this is saying is that if I take two parts of my fluid, here's a point, and suppose those 2 points are separated by lambda, this is how much the velocity is different between those 2 points. So if I go to smaller and smaller scales, this gets smaller and smaller, and you can see that the velocity gets smaller and smaller as you go down the cascade. The velocity fluctuations get smaller and smaller as you go down the cascade. So at this point, you could launch forward and you can ask, well, when is this applicable? What kind of astrophysical systems do we observe that demonstrate some sort of Coma Growth spectrum? what happens if the system is not incompressible. I've kind of assumed incompressibility when I was arguing for this, but you actually don't have to. But you do get different types of turbulence if you have strongly supersonic motions. You know, you get shocks and things like that. I didn't say anything about what if you had shocks along this cascade or something. So it's just a very clean physical picture. It's best thought of just like incompressible turbulence or weakly compressible turbulence, like low Mach number turbulence in a hydrodynamic fluid. So just any questions about just that? Yeah?
Maybe you mentioned now at the end, but that's the reason why the energy spectrum goes only with the kinetic energy. Or that also includes the thermal energy as part of the kinetic energy. When you can say that you have a velocity, like two velocity scales, for example, fluid velocity plus thermal velocity.
Right.
The thermal energy plus the kinetic energy.
Yeah. Yeah.
Okay. So that is because it's incompressible.
Yeah. Mm-hmm. Good. So what I want to move on to from here is what happens if you add a magnetic field. Right. So suppose we have this turbulence, but suppose now the fluid is conducting, say infinitely conducting, so it's ideal MHD, and we thread a magnetic field through the system. So you know, I've got my blobs, all these turbulent eddies, and I take a magnetic field, which is just imposed on the system, and then I ask, how does this change the character of the turbulence? So there's two things to note right away. One is that without this magnetic field, there were no preferred directions in the plasma, right? I didn't write down a wave vector, k. I wrote down a wave number, k. So there was some assumption of isotropy here. That if we go to sufficiently small scales away from the driving range, the turbulence is just isotropic. I don't need to speak of a wave vector. I could just speak of a wave number because every direction is the same. That could change, right? So if I introduce a magnetic field, if it's a strong magnetic field in the plasma, there's some obvious direction now. And the thing is, the argument in the Coma Growth case is that it's isotropic if I'm far enough away from the driving scale. So there might not be some isotropy at the driving scale, but if I go to far enough down the cascade, things will look homogeneous enough that I can just apply these arguments. That's not true when you have a magnetic field. All scales see this magnetic field, right? You can't, another way of saying this mathematically is that you can't Galilean transform away a magnetic field. So every single scale, as you go to smaller and smaller scales, they'll all see the field. And so there's some directionality which is established by the field, which holds at every single scale. So that's one thing that you have to deal with. So if we just enter, if a magnetic field enters the problem, one question you could ask is whether this isotropic wave number, whether we should split that into a k parallel or a k perp. Like, are there scales along the field? Are there scales across the field? Are they related to each other? Are they different? None of that is in Coma Growth theory, right? The second problem is now you're not dimensionally constrained anymore, because there's two velocities in the problem, right? There's instead of just u being your scale, or the velocity that you can use in your dimensional analysis, you have u, but you also have another velocity now, which is the alpha in speed. Right? So just to remind you, just b over square root of 4 pi rho. So now there's another characteristic speed in the problem, which means I can construct another time scale. So then I have to know, what time scale should I choose? Should I choose L over U, or should I choose L over VA? Those are two different time scales. So you start to have to make decisions. Coma Growth just sort of naturally emerges just from dimensional analysis once you make just a few simple assumptions. Here you have to start making choices. And so the first choice that was made was first done by Rezhnikov, but his paper largely was just not appreciated. It was followed by this guy Frightenin, who got the early credit until Rezhnikov's work started getting appreciated. And how they sort out these is, so there's this question here of how I take an isotropic wave number and I split it into parallel or perp. They don't do that. So I have a K in Coma Growth, and in IK theory, it just stays K. It's just still isotropic. So that's one choice that's made. Then the second choice that needs to be made is how to deal with two different time scales associated with these two different velocities. So in Coma Growth, you just have a single velocity. And the big difference came in the form of giving some primacy to the alphane time. So the alphane time being L over VA instead of L over U. In particular, I could ask, what's the alphane time at any given scale? How long does it take an alphane wave to cross some scale down the cascade? So right away, this is saying something about wave physics. I'm attaching something special to a wave. Over in Coma Growth, it was all eddies, right? I have some turbulent eddies, some large-scale fluid motions, which boil down into small-scale turbulent motions. Here, by attaching some significance to this alphane time, I'm starting to talk about wave physics. So there's some wave in the problem, which has a wavelength lambda, and you can cross that. It moves in one alphane time its own wavelength in distance. Everything else stays the same. So you still have some constant flux in an inertial range, and that's just by dimensional analysis given by this. So there's some velocity increment on scale lambda. So this is your energy, and that energy is passed down the cascade at some rate, which has to do with some kind of nonlinear time scale. And this is just the kinetic energy. So the only thing left to do in this theory is we just have to construct this nonlinear timescale. Once we can write the nonlinear timescale in terms of the things that are given to us, like the outer scale, the amount of energy that I'm pumping in, the amount of, or the strength of the magnetic field, once we can write this in terms of those given parameters, we know that this combination has to be constant, and that'll tell us how this scales with fluctuation wavelength. And once we know how U scales with wavelength, we can construct the energy spectrum out of that. So just like in the Coma Growth case, the turbulence is driven by these nonlinearities in the flow, right? The U dot grad U. This is, in the case of Coma Growth, it's these large-scale flows shearing other large-scale flows and boiling down to smaller-scale flows, which just shear each other. In the case of this Rezhnikov-Frightenin, like I said, there's something special about it in that now we've got wave physics. We have alphane waves. So what's going on here is there's some kind of fluctuation, which is like an alphane wave, at some scale, and there's some fluctuation, like an Alfvén wave at perhaps some other scale, and the two are nonlinearly interacting with one another, right? This one advects the other one, or shears the other one, and that's how the turbulence gets to smaller and smaller scales. And so if I want to know, what I'm looking for is this time scale in order to get the cascade. So this thing right here, the size of that nonlinearity in the inertial range is just there's some amplitudes squared and there's some gradient. I'm just going to order, this is how turbulence works. You just twiddle everything. If I want to know, how much does this fluctuation change? In just one nonlinear interaction. How you do that is you take this nonlinearity and you just multiply by a time. And like I said, the time in the problem is this lambda over VA. And the reason why to multiply by a time, remember the left-hand side of the momentum equation was du by dt, so a linear term and the nonlinear term. And if we ask, how much does this change because of this nonlinearity in some time, it's just the size of this multiplied by some characteristic time. And the assumption is that the characteristic time is the Alfvén time. So that's the assumption. So at this point in the analysis, there's another assumption that's made. And that's something that brings us to something called weak turbulence. And the idea is that there's a wave packet which is moving along. There's some other wave packet. There's some nonlinear action between those wave packets, which are Alfvén wave packets. One of the wave packets changes by an amount, which is roughly like this during that interaction. But this is actually a small change. And that's why it's called weak turbulence. In any one collision between different wave packets, the nature of any one of those wave packets does not change much during one collision. And so if you want to get a nonlinear time, like the true nonlinear time for a wave packet to be ripped apart and cascade to smaller scales, you need to figure out how many collisions it takes to take that wave packet and rip it apart and cascade to small scales. So this is just for one collision. And so from there, they adopt a random walk argument. They say that suppose I have some wave packet, it's moving along the magnetic field, it encounters some other wave packet, they undergo some sort of mutual interaction. That changes the wave packet by this amount. And then I'm going along further, and I meet another wave packet that I'm going to interact with. And the assumption is that every single one of these collisions is uncorrelated. So then there's an assumption here that the subsequent interactions are all uncorrelated. And what this does leads to a random walk accumulation of changes to your wave packet. And then so what you want to ask is how many of these uncorrelated interactions does it take to significantly distort this wave that I'm following, right? So I have this wave packet, it's going along, it's colliding with a bunch of other wave packets, they're nonlinearly interacting. How long does it take for that thing to be really disturbed? And so the argument is this random walk argument is like this. So this is the change in the wave packet during one collision. If they add up just a random walk, I just have a root n change. So the number of collisions required is going to go like the wave packet fluctuation amplitude at that scale divided by how much is going to change in one collision, and then square it. And this is just random walk scaling. You know, things go like root n, and so I'm just squaring both sides. Good. So if I put this formula in right here, so that's the number of collisions. Now, this ties back into this weak turbulence. So you see, I was making some argument about there being a lot of collisions in a wave packet in order for it to be significantly distorted. That's also a statement about the size of these fluctuations. So if n is really big, that's saying that the fluctuations I'm interested in are very small amplitude. So the idea is that you've got very small amplitude waves, Alfvén waves, which are running around field lines. They're interacting with each other through this nonlinearity. Every time they interact, they change just a little bit because they're small amplitude. After n of these interactions between these wave packets, you've changed one by something of order itself. So I'm going to take that. I want to leave this board there. I'm going to take those arguments and construct this nonlinear timescale. So this nonlinear timescale is simply these number of collisions times the Alfvén time. Every single collision happens on something like the Alfvén time. There's n of them. So the nonlinear time is just the product of the two. And so I just take that formula there. And then I take this formula for tau A. And now I have the nonlinear timescale. And so all I need to do is now take this nonlinear timescale, sub it into this formula for the energy flux, which I assume is constant. So if I take that and I combine these two things, I get this. So it's a different scaling than Coma Growth. It's still isotropic. There's nothing here that says parallel or perp. There's just a scale, but the scaling's different because the nonlinear time is different. Once you know this, it's straightforward to obtain the energy spectrum. You just take this formula. You see that U goes like lambda to the 1/4. And I just have to use this, right? If I integrate over all the energies at every k band up to some scale that I'm interested in, I get the kinetic energy living on those scales. I just take that and I plug it in here. And what this gets me at the bottom of the board is what's called the Rezhnikov-Frightenin power spectrum. And you see it's different. It's 3/2, not 5/3. Good. So that's a prediction. And this prediction was pretty much just considered to be true for about 30 years. There started to be some reasons to doubt it when numerical simulations came along, right? One of the first things that emerged from the numerical simulations is that isotropy was not a good assumption. And that started casting doubts on this. That led to something called Goldreich-Streethard turbulence, which is what I'll talk about now. I'm going to leave this scaling on the board because even though it's technically wrong now, for some reason, some simulations give k to the minus 3/2. So I'm just going to leave it here. That involves another Russian, Stas Boldarev. So you can see this is, I suppose, where you should talk about these things. Okay. So this was like 65, something like that. There was I think Ryzhnikov was 65, Frightenin was 67, I think. So then 30 years went by. There were some doubts cast on the isotropy assumption. So Goldreich and Streethard's answer to this was to take the Coma Growth K and actually distinguish between the length scales of these fluctuations along the field versus across the field. And one reason for that, like I said, was from simulations. When you looked at a twisted magnetic field and you looked at the fluctuations on that magnetic field, they kind of have, the eddies have a shape like that. They're not balls. Like there's a definite elongation. And for good reason, because magnetic field lines have tension, right? They don't like having ripples along themselves. But they don't really mind that much having ripples across themselves. So you're allowed to have smaller scales across field lines than you are along field lines. It's just natural because there's some elasticity associated with the field lines. But this gets us back to the problem. If you're going to distinguish between parallel and perp, you need some way to relate them. Because in Coma Growth, you use everything at your disposal, and just dimensional analysis gives you the answer. In a Ryzhnikov-Frightenin, you had to make two assumptions. You had, they just took k to be isotropic, so it's the same. But then you had to argue something about what the new timescale is, what the new nonlinear timescale is. Here, we've abandoned that first assumption, which means you need some way to relate k parallel and k perp. And this is now known as critical balance. And with some modifications that I'm not going to get into due to Stas Boldarev, and most recently Alfie Mallet and Ben Chandra and Alex Shekashikin has done some work on this. This is pretty much modern MHD turbulence theory. It's just accepted now. A lot of the predictions out of what I'm about to show you have been spectacularly proven in numerical simulations. There are some weird things. Like I said, what's going to come out of this is a 5/3 spectrum, but some simulations still show a 3/2 spectrum. And so this led people like Stas Boldarev to make some adjustments to this theory. I'm not going to go into those adjustments. I'm just going to give you the original Goldreich-Streethard picture. So the idea in this critical balance is to relate k parallel and k perp because they're unknowns and we need an equation to close the system. And the idea is that the linear timescale in the problem is of order the nonlinear timescale in the problem. And this is what's called strong turbulence. In a Ryzhnikov-Frightenin and other theories of weak turbulence, this nonlinear timescale is not on par with the linear timescale. Remember, it took many Alfvén wave collisions for that wave to be altered by the nonlinearity. Here, it takes one, right? The nonlinearity is comparable to the linear timescale. So the wave propagates and it nonlinearly gets disrupted on the same timescale. And so here that the frequency of just a shear Alfvén wave is omega equals k parallel VA. So that says that this timescale, yeah, this time scale is L parallel over VA. And this nonlinear time scale comes from this nonlinearity, u dot grad u, right? And there's an assumption that's about to be made that you can verify after the fact, which is this, that the eddies are elongated along the field lines and have short scales across the field lines. And what that means is that this gradient is dominated by its perpendicular component, right? K perp is much bigger than K parallel. So this gradient is the dominant gradient, which means that the nonlinear time scale is associated with L perp. And so this is the critical balance. So this is how the fluctuation amplitudes are related to the alphane speed through the anisotropy of the eddies. So this is what joins the parallel and perpendicular scales together. And where we go from there is just the Coma Growth argument. So you say that the energy flux is a constant, that we're primarily concerned with fluctuations that are perpendicular to the magnetic field, like a shear alphane wave. We know that this epsilon is u squared on some scale divided by some time scale. And now we know what the nonlinear time is because of critical balance. It's just the linear time. So this is just the linear time scale. And the linear time scale is just that of an alphane wave. Well, it's also the nonlinear time scale. So this is L perp. You know, I've been kind of screwing with notation. L perp is denoted by this lambda. So lambda divided by delta U perp on that scale. And what you can see from this is you actually get the Coma Growth scaling, and, but not isotropically. It's only in one direction, because I have delta U cubed divided by scale is constant. And over here, I had U cubed divided by scale is constant. And so you get the same exact spectrum, except it's only in the perpendicular direction. So now I can erase this. So that's the Goldreich-Streethar power spectrum. It's Coma Growth-like, but only in the motions that are perpendicular to the fluctuating magnetic field. And then I can come back here and get the relationship between the parallel structure and the perpendicular structure. So that right there, the critical balance, just says this at a given scale. This goes like, it's getting hot in here. All the windows are shut now, aren't they? Yeah. If it doesn't bother you too much. So those velocity fluctuations go like k to the minus third. So this just goes like k perp to the 2/3. And that's the other prediction of Goldreich-Streethar theory. So you've got an anisotropic cascade, which is Coma Growth-like in the perpendicular direction. And the eddies go like this. And what this means, good, I'll take both. What this means is that as you go to smaller and smaller scales, so larger and larger k perp, the anisotropy gets bigger and bigger, right? So even if you start with relatively isotropic turbulence at the outer scale, you don't keep it. The smaller and smaller scales get more and more anisotropic. And that's the distinguishing feature of strong turbulence, strong MHD turbulence, as opposed to Coma Growth or this weak turbulence theory. So the history from then is that people started looking for this in simulations. There was a bit of ambiguity because they were looking, this is not particularly constraining. It's 5/3, just like Coma Growth, but this is. This is a prediction that can be tested. There was some difficulty, though, because technically this parallel and this perp are not with respect to the magnetic field that you thread the plasma with, but with respect to the exact magnetic field, which is wiggling. So you actually have to measure parallel and perp relative to a wiggling field, which is tricky. But eventually, there was like a Cho and Vishniak paper and some work by Alex Lazarian and collaborators confirmed this in simulations. So this is sort of just now accepted until recently when it started to come into doubt because there's some simulations that show this to the -3 halves. So things are still slightly in flux. There's been some recent clarification. But pretty much, if you want to understand modern theories of astrophysical turbulence, it really starts with Goldreich-Streethar and this theory right here. So I thought I'd go through that because it's sort of fundamental for modern turbulence theory. Is there anything more I wanted to say? No. That's all I wanted to say about this type of turbulence. Please ask questions. Yeah?
How does the strength of the magnetic field factor this? Is that at all?
No. But it matters what the strength of the amplitudes are. And the reason why is in an Alfvén wave, delta U over VA is of order delta B over B naught. That's like an eigenvector for an Alfvén wave. So this critical balance here is saying something about, it's relating the anisotropy of the fluctuations to the fluctuation amplitudes. And because the fluctuations are Alfvénic, it's saying something about the perturbations, the size of the perturbations of the field. And something which isn't always appreciated is that this can be small, and you can still have strong turbulence. So in weak turbulence, this is a very small number. In small turbulence, this can still be a strong number. But what accounts, or a small number, but what compensates for that is the difference between L parallel and L perp. So even though you can have small amplitude fluctuations, the nonlinearity can be big if, even though these U's might be small, the nonlinearity can be big because of the size of K perp. Remember, you can make very sharp structures across the magnetic field lines, and that increases the size of this nonlinearity even though the fluctuations are small. And so this doesn't really say anything about, I can have Goldreich-Streethar turbulence in a strong field or a weak field just as long as the fluctuations satisfy something like this. It even does pretty well if you do that, even though it's not formally or not rigorously argued for. And then, of course, this cascade goes down to small scales where things like viscosity and resistivity become important. I'm not saying anything about that right now. Just wanted to get the spectral slopes. Yeah?
Then you would have like these turbulent eddies in a preferred direction.
Yeah.
And they would be perpendicular to the field line?
So each eddy would be described by a K parallel, which is telling you its extent along the field, and a K perp, which is telling you its extent across the field. And all of these wave packets would have very small scales across the field and very long scales along the field. Yeah. And you can see this quite clear visually. I mean, it was even very, very poorly resolved simulations, like in the mid-'80s, started to cast doubt on this. I mean, you just visually look at the fluctuations, and they're extended. As soon as you put this on a computer. OK, good. So then what I want to do now is say, suppose you've got turbulence, but the magnetic field is not strong, in the sense that you can't really define a well-posed direction. There's not a guide field in the plasma. So there's a very old question, which is I take a conducting fluid, I put a very weak seed magnetic field in it, and I just start stirring. What happens? And this is one example of something called a dynamo. Under certain conditions, the magnetic field will grow. Under certain conditions, it won't. And the earliest theories of this were just trying to sort out under which conditions the field would grow and which conditions it wouldn't grow. Without calculating anything, there's one thing that you can establish pretty well, which is if the host plasma is really poorly conducting, it'd probably be hard to stretch the field, right? You try to you stir the plasma, the magnetic field will try to move because of flux freezing, but if the flux freezing is really poor because the conductivity is low, the magnetic field is just not going to be amplified. So some of the questions that go into this, whether it actually equals a dynamo, have to do with something called the magnetic Reynolds number, which I mentioned the first. I don't think I mentioned this. Or yeah, I did. Well, this. So it's a measure of the motions that you're stirring, the length scales on which you're stirring them, and then the resistivity. And generally, if you want a dynamo, this needs to be big. There's a lot of work that goes into establishing what the critical Reynolds number is for you to actually grow the magnetic field in such a situation. It can be like 10 or 100 or something like this, but it's bigger than 1. What that means, being bigger than 1, you don't want the scales on which you're stirring. I mean, you want the scales on which you're stirring to be conductive, or else nothing will happen, right? The second question to ask leads us to things called anti-dynamo theories. So there's certain constraints that the stirring or the system have to satisfy in order for you to actually be able to grow the magnetic field, just based on topological constraints. So these here are topological constraints. This here is just a constraint on the host plasma. This is an actual topological constraint on either the motions or the magnetic field or something like that. So I wanted to sketch something really quick here about the second part, which is due to Zildovich. It's called the Zildovich anti-dynamo theorem. And then I want to sketch a calculation that he did. When did he do that? It's like at some point. Yeah, 86. To show how a dynamo might work in this kind of environment. Are there any questions about just how, like, it's a fairly simple problem to pose, right? I have a fluid, I put a seed field in it, I stir. Does the field grow or decay? It can get very complicated. You can ask, what does the resulting field look like? What are its statistics? How far does it go until it stops growing? I'm not going to deal with any of that stuff. So there's a Zildovich anti-dynamo theorem. And this says just basically that it doesn't work in 2D. And the proof is very, very simple. If you're in 2 dimensions, you can write your magnetic field in terms of a vector potential like this. And that vector potential can just be a scalar in one direction. Here's just the MHD induction equation. This is just the ideal term that carries the magnetic field around with the flow. And this was in Phil's talk about dissipation. This is just ohmic dissipation. This is the coefficient that goes into that magnetic Reynolds number. And you can see that if I need a dynamo to work, this can't be dominant on some scales, right? Or else you'll just dissipate the field. If I take these two together, you could just do some vector algebra. And you get an equation that looks like this for the scalar A. And if you take this and you just square it and then average over volume, this term is going to go away. This is just advection, right? So this is just conservative advection of A by the flow. It's just carrying it around. If you integrate over volume, this is just going to go away. And then all you're left with is this. And after some vector identity, yeah, you get this. So integrated over volume, this equation, this A is just going to decay. So that means in time, you might have some temporary growth of the field, but in the long time limit, in terms of a box average quantity, the magnetic field is going to decay in time. And this is all because of being able to write the magnetic field like this, which is some statement about being two-dimensional. Good. So then he did another neat calculation that I'm not going to take you through. It's in the notes. I'm just going to give you the starting point and the ending point. Let's see how long it's been. An hour. OK. So suppose this dynamo were to work. All we've shown is that it doesn't work in 2D. OK, fine. Let's do it in 3D. Does it work in 3D? If it were to work, the idea is that we drive velocity at some large scale. There might be some kind of cascade. And here is the resistive scale down here. And then dynamos at this point fall into different classes based on where the viscous scale is. So this is the scale that dissipates the magnetic field. There's also going to be a scale that dissipates the kinetic energy, the velocity field. And it could be over here. It could be over here. In many hot astrophysical plasmas, it's over here. So this would be a viscous scale. This is a resistive scale. So here's your velocity field. There might be some energy injection, some inertial range that might look Coma Growth or not, some dissipation, which happens due to viscosity. And then the question is, where does the magnetic field grow and what does it look like? I'll just give you the answer. At early times, this is B, this is U. It looks something like that. Yeah? Not MHD dynamos because there's no particles in MHD. But yeah, in principle, yeah, if you had a collisionless dynamo or weakly collisional dynamos so that you could get away from having a Maxwellian, you could accelerate particles to non-thermal energies. That's not been shown. Yeah. So I think just, what is it? Yes, wait, what's today? Tuesday. Yesterday, I posted a paper to the archive with a PhD student where we did collisionless dynamo with a PIC code. But we didn't really see a lot of non-thermal stuff. But it's also non-relativistic, and sometimes you need relativistic effects to accelerate particles. So it's open. So there's some theory that says that this slope right here is k to the 3/2. It's due to someone named Kazantsev. It's called a Kazantsev spectrum. I'm not going to go into where it comes from. It's actually hard to derive. What I'm going to sketch is just a proof that this actually happens. That if you stir here, and that there's a viscous scale here, that you will generate magnetic fields, yeah, full stop, in 3D. By the way, this, you might have heard of a Prandtl number before, which is viscosity over resistivity, or equivalently, the magnetic Reynolds number divided by the just fluid Reynolds number. And in this picture that I drew, this is bigger than 1. In other words, you hit the viscosity before you hit the resistivity. And most hot astrophysical plasmas are like this. So the intracluster medium, the hot phase of the ISM, certain classes of black hole accretion flows, they're all high PM systems where the viscosity is bigger than the resistivity. Sometimes by a lot, like 10 to the 29 or some crazy number like that. Yeah, I think like in galaxy cluster plasmas, the kinetic energy Reynolds number is like 100. And RM is, at least due to Spitzer resistivity, RM is like 10 to the 20 something. So this is a huge number. Right, so how it goes is that on these scales, I worked this out in my notes, the velocity looks locally linear. So on viscous scales, so the velocity fluctuations on the viscous scale are locally linear. And the way that Zildovich's calculation goes is that we're going to Taylor expand the velocity field at that scale about some position. And you can show under certain circumstances that this will grow. And I just want to sketch that and then move on to the last bit. Good. Anyone ever hear of Cowling's anti-dynamo theorem? Hands up, yes, no, okay. One person, okay. So there's a variety of anti-dynamo theorems. So Cowling says that you can't amplify an axisymmetric magnetic field. This is really important in accretion disks, because like the MRI can operate as a dynamo. So there's some sort of constraint on the topology of the magnetic field or the topology of the flow that come into these anti-dynamo theorems that dictate whether something like the MRI can actually survive and amplify a magnetic field in long-term limits. So this is just one of them that pertains to what's called a turbulent dynamo. Yeah. All right, so well, not K. Do what's in the notes. So remember, I said what I'm going to do is Taylor expand the velocity. So I'm going to go to a local patch. I know that the flow is linear, or close to linear, and smooth, which means it's differentiable. And so I'm going to expand that velocity field. So I is just an index for the component of the vector. So at some position, I'm just going to Taylor expand about some position, just labeled 0. And this is just the derivative of the flow, right? It's a Taylor expansion. So there's a derivative right here. And this is just called a shear tensor. Shear because the velocity has a derivative that's called shear. And then there's going to be a lot of GR later. So you should get used to summing over indices if you don't already do that. And the idea is really simple. It's let's just take the induction equation. Sorry. Use a vector identity to just write out all the pieces. And just take this and substitute it in for the velocity. So there's different terms here. This corresponds to advection. So the magnetic field is carried around by the flow. This is just the magnetic field being stretched by gradients in the flow. This is the magnetic field being squeezed by divergences or convergences in the flow. And then there's dissipation. And we haven't said anything about the form of this tensor yet, right? It might be just something that compresses the field, or it might be something that stretches the magnetic field, or it might be something that just carries the magnetic field around. The important step to notice, though, is that there's no back reaction of the magnetic field on the flow. Like, I haven't said how this flow is going to respond to there being a magnetic field in its presence. So this thing is called a kinematic dynamo. It's that the flow that you're considering is not affected by B. There's no back reaction because of a Lorentz force, which means I'm just going to specify U. Suppose I know it. I'm just going to specify it. I'm going to say for this velocity field, is the magnetic field amplified or not? So I'm not going to do this. It's in the notes. The way this works is you just take this, you substitute it in, and you look at this equation component by component. It turns out that you can take plane wave solutions. The induction equation is linear. And you just take these plane wave solutions if your k is time dependent. Physically, what that means is that the scales are going to be changing, right? Like I take a rubber band and I go like this. Its scales are changing in time. So its scales are a function of time. So you just substitute this Fourier decomposition in. You get a constraint on how k is supposed to evolve, and you get a constraint on how b is supposed to evolve. And you can actually solve this for certain types of tensors. And the notes, I do it for a very simple diagonal tensor. And you can show that in certain systems, under certain conditions for that flow, the magnetic field grows exponentially. So you can show that the volume average magnetic field can grow exponentially. And this growth rate here is a function of what this looks like, the stress tensor looks like. But you can actually get a closed analytic formula, which is really cute. So this was less about teaching you a calculation, more just educating you about its existence. You know, if you really want to follow up on it, it's done in detail in the notes. paper, Zildovich's original paper is also referenced if you want to dig even deeper. You can follow the paper trail from there. But this is more about just exposing you to something that you might not have seen before, involving any dynamo theorem, something called the kinematic dynamo, and something about what the field may or may not look like based on something called the magnetic Prandtl number. So if you just take those things away, that's great. Like I said, if you want more, the details are in the notes. I just wanted to close with one more thing, and that's going to help you out when or if you continue playing with this PIC code that we've made available. And usually the topic I'm about to talk about is completely divorced from these last two topics, right? These were turbulence and dynamo, and what I'm about to talk about are kinetic instabilities. But in modern astrophysics, these two things are really well tied together. And I wanted to show you, just explain to you how in sort of some work in modern theoretical astroplasma physics, if you want to do something like dynamo or turbulence, you also have to know about some kinetic instabilities that I'm going to talk about. And the motivation for this connection is really, really simple. And it goes back to something I said in the second lecture involving particle motion. So you can understand the connection between these complicated things by just considering a single particle. So it's quite nice in that respect. Suppose, go back to that second lecture, and I had a particle that was just doing this. So it's just a single particle going around a magnetic field line. And I can ask things like, well, what if I change this magnetic field like I was doing in the turbulence and in the dynamo? How does this particle respond to this changing magnetic field? And if you had a decent classical mechanics training in undergrad, which I didn't, you might have learned about adiabatic invariants. I didn't. So it's OK if you haven't heard of this before. It's just a function of your teachers. So I don't blame you. But there's these things called adiabatic invariants. Well, first of all, has anyone heard of them? OK, so that's better than Landau damping, at least. So the general form of this, this was actually, I think, mentioned by Einstein. Actually, you know about this. Have you ever taken an undergraduate course in quantum mechanics? You actually know about this. Because you know that E over omega is h bar. All adiabatic invariants look like this. So there's some energy divided by some frequency. And this is something pointed out by Einstein in like 1911 or 1915 at some conference. And if you have some kind of energy in your system, and there's some sort of frequency describing a time scale over which that system evolves. Like maybe if you took quantum mechanics, you might have seen something like if you have Griffith's book or something. There's a chapter on adiabatic evolution of a wave function. And it's what happens if you take like a particle in a quantum mechanics in a square well, and you slowly move the walls of the square well. There's an adiabatic invariant there. And it has to do with the frequency at which you're moving the walls and the energy associated with the wave function. And this is approximately constant. Really simple experiment you can do is take a pendulum that's going back and forth and just slowly make it longer and ask, what's the conserved quantity if I do that? And it's this. There's these things called Poincare invariants, which are that this is exactly constant. You get those in Hamiltonian mechanics. The approximate version of that is adiabatic invariance. So this right here is saying something about the size of this frequency, right? I mean, if I take a pendulum and I just take the length of the pendulum from 10 centimeters to a meter in half a second, things aren't going to be conserved, right? But if I do this really slowly, in other words, if I lengthen the pendulum at a rate which is slow compared to the oscillation frequency, you'll get this, this satisfied. So then let's just apply this to this particle system. I had to teach adiabatic invariants. All right, so you can ask, how much energy does this particle have as it gyrates about the magnetic field? And that's very simple, right? So there's a particle. The Lorentz force is in the perpendicular direction. There's some energy associated with the gyro motion. That's that. There's a periodicity in the system, so there's a frequency. Done. Okay. So this is QB over MC. And if this is roughly constant, you get this. And so what this means is that if I take a particle in a magnetic field and I slowly change the strength of the magnetic field, the perpendicular energy of this particle has to change. It's actually something like a Lenz's law. You can think about this a few different ways. One is angular momentum conservation. You can think about it. What's angular momentum? M v perp r, right? What's the radius, the gyro radius? It's that. So it's like angular momentum conservation for a particle undergoing an orbit. If the magnetic field strength changes, the frequency changes, you have to change your velocity accordingly to conserve angular momentum. Same kind of thing. It's just adiabatic. So if you change B too quick, you're going to break the system. Good. So then you can ask, the two examples that I just gave, you're taking a magnetic field and you're doing nasty stuff to it, right? You're ripping it around, you're compressing it, you're stretching it. This thing is going to be changing all over the place. So what are the particles doing? Well, in MHD, they're doing nothing. You don't have that because collisions are just randomizing the velocities of the particles all the time, instantaneously as far as MHD goes. You change this in MHD, this does not care. Because this particle is not doing that. It's getting kicked all over the place by collisions. But if you had a collisionless system and you changed omega, you're going to have to change the way the particles behave. So what's temperature? Temperature is just something like the expectation value of v squared, right? It's the mean. It's that. It's a measure of the random motions of the particles. Expectation value of v squared minus its mean squared, right? So what does this mean is that if I change B, I have to change T perp. And in collisionless plasma, what that means is if I take an isotropic Maxwellian and I thread a magnetic field through it and I change that magnetic field, it's not Maxwellian anymore. And a whole bunch of nasty things can happen when you're not Maxwellian. You don't really learn that in StatMech because like the StatMech that you take in undergrad is all, you're in thermodynamic equilibrium. Something like this is going to push you away from thermodynamic equilibrium because you're not Maxwellian. So I just want to show you, I'm not going to derive them. They're derived in the notes. That's not what I'm here for. But I'm going to tell you about two violent things that happen when you do this. And then you'll be able, there's problem generators for the code. If you want to see what they actually look like, these instabilities, you could just do it. So I'm not going to derive anything. I'm just going to write down two pictures, state their names, and just tell you physically what they are. OK, I'm at an hour 20 right now. OK, so I'll finish up. So one is something called a Firehose instability. And I'll put that there. And here's something called the Mir instability. And these instabilities basically come from this. So suppose at t equals 0, I have a distribution function which looks like that. It's just a Maxwellian with some normalization. And if I change the field strength and I keep these adiabatic invariants, it's not going to look like this anymore. So another way to write this, because there's a magnetic field involved, is like this. I just split V into V parallel squared and V perp squared. Now I know that V perp squared has to adjust because I've changed B. And what happens is you get a distribution function which looks like this. It's called a bi-Maxwellian. So it's Maxwellian in the two directions, but you see the temperatures are different. So if I had contours, that's not a circle. So if this is Maxwellian, that's a bi-Maxwellian. There's two different directions, have two different temperatures. The width of the Gaussians are different in different directions. And if you have that, and you have something like this. So if the difference in these two temperatures, so in an isotropic Maxwellian, that left-hand side is 0, right? It's isotropic. So this is 1, minus 1 is 0. If there's any difference in this ellipse, and if that difference in magnitude is bigger than something that relates to the magnetic pressure and the thermal pressure, like the plasma beta, and if you try to propagate an Alfvén wave into this system, it's not going to propagate. It's going to explode. This thing is going to go unstable. And the way to understand this is just by virtue of its name. Suppose you take a fire hose and you turn on the water pressure really low. There's some tension in that fire hose, like there's tension in a flux tube, and there's some pressure of the water shooting down the tube. Now, if you crank up that pressure and you just shake the line a little bit, it'll just kind of go like this, and you'll send waves down. But if you crank the water pressure way up, it'll just start flapping. And that's what's happening here.
Only at scales of ion, your radius.
Yeah, I'm not saying this yet.
So it will operate only at scales of ion.
No.
Your radius.
Scales above the ion Larmor radius, but not scales at the Larmor radius. Yeah. So this holds for k rho I less than 1. Yeah, we can talk. These are details that I don't have time for. So this is an Alfvén wave with an effectively negative tension. So tension field lines are supposed to be restoring. What happens is that there's an extra anisotropy in the pressure, and that anisotropy undermines that restoring tension, and the thing just goes unstable. And then there's a Mir. Sorry. 4. Just something like this. And it happens if you have something that looks like a slow mode magnetic perturbation that has compressions in it. What happens is that you accumulate a whole, when you squeeze, it's like a sausage. When you squeeze, stuff comes out. So if you squeeze these field lines, stuff shoots here, and if that stuff has a lot of perpendicular pressure, it blows the field lines out. Right. Good, thanks. I'm trying to skip through this stuff fast, so I'm just skipping stuff. So thank you. It's called mirroring because if you're a particle that's moving this way, well, it's like the Russian border. Only certain people can get through.
It's U.S. border.
That's the U.S. border. Well, actually, No, because at the US border, what would happen is you would come here and then you would sit there for 5 hours. But the Russian border, they just know if you're getting in or not. No. Right. So, yeah. Yeah, so you come in. Only particles that have certain pitch angles can go through here. And what happens is that those particles that have large perpendicular energy can't get through. And what happens is that all those particles with large perpendicular energy just get stuck in this trap, in this potential well, and then they've got large perpendicular energy, so they just blow out. And well, okay, magnetic tension and pressure can be restorative, but if this is bigger than this, those restorative forces are undermined and the field lines grow. They grow out to be even bigger. The gate gets harder to get through because the potential barrier is bigger. You just get trapped more. You blow the field lines out more, and the whole process runs away. And this thing is also so these things operate on Ion-Larmor scales or just slightly above Ion-Larmor scales. I derive them in the notes so you can actually see the calculation. Or if you don't like calculations, you can just use the code and actually visualize them. And sort of one aspect of modern astrophysics is figuring out how things like turbulence and dynamo behave in collisionless plasmas. In collisionless plasmas, you're not guaranteed to be Maxwellian. So you have to worry about things like when the temperature is not isotropic and you get instabilities like this. So I'll stop there. Sorry, it's like 4 topics thrown at you, or 3 topics thrown at you. But like I said, the idea is not to overwhelm you with details. If you want to be overwhelmed, just look at the notes. The point is just to expose you to these things, which you might not have seen before. And if you find any of them interesting, you can follow up in the notes and follow the paper trail from there. Right. Thanks. Yeah. Yeah.
Sure. Weak magnetic turbulence. If the magnetic field is sufficiently distorted, could the assumption of enabling isotropic be kind of valid?
Yeah, but some of the other assumptions of weak turbulence wouldn't be. So weak turbulence, so you need delta B over B to be small. So you need the magnetic fluctuations on top of the mean to be small. And so it depends when you say if the magnetic field is sufficiently complicated. What do you mean by that? And that usually violates delta B over B being small. But yeah, that's a good question because tangled magnetic fields, assuming that they endow the plasma with some kind of isotropic properties, is quite an attractive line of thinking. Like Mikhail Medvedev, who's here, did some paper where suppose you take a magnetic field and you tangle it, and you can ask, how does heat get conducted from one side of that magnetic field to the other if there's a tangled mess in the middle? And so yeah, there are questions about if you have a tangled magnetic field, whether things behave quasi-isotropic, but not in weak turbulence.